Okay, so this example or this video is going to take us through the idea of rotating a pail of water, a bucket of water in a vertical circle. So by vertical circle, earlier we looked at a horizontal circle, which looks like this. So say that you have something attached and it's going around this way, that'd be a horizontal circle. But instead we're looking at a vertical circle this time. So we're bringing something and we're circling it above our heads, below us, and back around. Very specifically, we're talking about a pail containing water. And so if you've ever actually done this, it's a pretty cool phenomena. At the very top, if you are doing it fast enough, the water stays in the bucket. We know that gravity would want to make the water come down, but if you're spinning fast enough, you can actually make it to where the water stays inside of the bucket. And so that's what we're going to be looking at today, is that idea. So the first thing as we look at this, it says draw a free body diagram for the top. There's a step that I added in for you guys as we talk about this because that should always be your first step. You're doing anything with forces, draw a free body diagram. So my free body diagram, I'm going to add a little bit more to it than we normally would. But that's just so we can have a really good visual. So first off, we're talking about our pail. It's upside down because we're at the top. So I'm going to get rid of the handle, but now you have that idea. And we're dealing it with the water actually being at the top of the bucket. So I'm going to put my water in so that you can see it. So if we look here, we know that we'd have the force of gravity going down because the force of gravity always goes straight down. And that would include the mass of the whole system. The other thing that we would have here is the water. So we're looking very specifically at the water itself. And I know that if the water is pushing onto the pail, then the pail is also pushing back onto the water. So that would be our force normal in this situation, would be the pail coming back onto the water. So if you're looking at this example other places, every once in a while you actually see that written as force of pail on water, and that's what they're talking about here. So before we're done with this, we always want to ask, do we need components? And so a reminder that your components need to be parallel and perpendicular to your acceleration vector. So then our question becomes, okay, well, where's the acceleration vector here? And so you have to think about the path of motion for that. Well, we know we're going in a circle. It's not my best circle in the world, but that would kind of be the path here. Well, in a circle, you have AC. Your acceleration is pointing towards the center of the circle. So at the very top, the center would be straight down. That would be my acceleration vector. So now I look and I see really easily that, I don't know why my thing isn't working. Okay. All right, sorry about that. My laser that I like to point with for some reason is not working. I was going to show you guys right here, so now I'll just draw instead. We can see that our acceleration and our force of gravity are parallel, so we are in the same direction. We are good to go there. Aha, ooh. Okay, I give up. I'm going to go on, keep teaching with you. I'm sorry that I was putzing around with that. So now we can go ahead and keep going. And it says, find the force that the pail exerts in the water. So we're dealing with this idea of the force normal. Whenever it's asking you to find a force, do a sum of forces equation. So I can come in here and say, okay, the sum of forces in the centripetal direction, because both of those are pointing towards the center of the circles, they are in the centripetal direction. Because they're both pointing towards the center here, we would say Fg plus Fn equals MAC, because they're going in the same direction. So Fg we know is mg plus force normal, m, and then AC we know is v squared over r. So if we were to rewrite this around, we end up with force normal equals m times v squared over r minus g. Now, the weird thing with a circle here is that, with a vertical circle, is that your sum of forces is going to be different at each different point. because gravity is going to look different. At the top, gravity is going down, which you're like, okay, yes, that makes sense. But the acceleration vector is also pointing down. When I'm over here, my acceleration vector is pointing in, but my gravity is still pointing down. And so gravity is going to look a little bit different. You'd have to break it up to get into your sum of forces centripetal, depending on where you are in the circle. So it's really important, just the way that we handle that, is that this was the force centripetal. And you can say at the top, we're dealing with it at the top here. And so over here, I would go ahead and say top as well. So at the top, our force normal, so that exertion of the pail onto the water is equal to m, v squared at the top, over r minus g. We're going to use this formula on the next page as we move on. So what we're talking about is how can we make it to where we actually have the water staying at the top? How can we actually keep that water at the top? Well, if we go back into the diagram, you kind of got to think about the real world here. If the water is staying in the bucket, then it's staying up here at the top. And if it's staying up here at the top, that means that the force, there is a force of the pail back onto the water because it is up there. But if the water is slipping out of the bucket, so say that it's come down to the middle of the bucket, notice it's no longer in contact, so therefore there is no longer a force normal. So pretty much all we're saying here is that if we wanted to stay up here, there would actually be a force normal. We need to be able to see that force normal there. Here, there's no contact, there is no force normal. So that is the stipulation. It says what needs to be true for the forces at the top for the water to remain in the pail. What needs to be true is that there needs to be a force normal. The water needs to actually be hitting the bucket. So we can use that to go ahead and solve for the velocity at the top. We know that when we're trying to find a minimum or a maximum value, we use that critical point and we set it equal to either, so with friction, we set it equal to that maximum static friction. Here, we're going to set it equal to 0. So if you're ever trying to surpass something, it's what are you trying to surpass? That's what you set it equal to find that minimum or the maximum. So we're trying to surpass 0. We want there to be a non-zero, a positive non-zero force here. So we need to be greater than 0. We're going to set it equal to 0. So once again, we're saying that the force of the pail of the water, which we're calling force normal, needs to be greater than 0. So therefore, to solve this, we're going to say the force normal equals 0, which on the other slide we saw was m, v at the top squared over r minus g. We can solve this out because we're asking for the velocity. We're trying to find the v top. So I'm going to divide both sides by m. Well, that just gives me 0 equals v at the top squared over r minus g. I can bring the g over. Let me zoom in so I can write a little bit more. I can bring that g over, which gives me g equals v at the top squared r. We now bring the r up, so we get rg equals v at the top squared. So we would say v at the top has to be greater than the square root of rg. So the minimum value would just be the square root of rg. So now you can see how it is related on that velocity. If you've ever done this phenomena before, you know that you have to swing it fast enough. If you don't swing it fast enough, the water is going to fall out. And this is actually that minimum amount of whatever your radius is times the acceleration of gravity and the square root of that. That's going to be that minimum velocity you have to do to keep the water inside of the bucket. Notice mass immediately canceled out, so it doesn't matter how much water you put into the bucket, that cancels out. It just means you have to maintain this speed, or you have to reach this speed by the time you get to the top. So we looked a lot at the top because it's kind of cool, but as I mentioned on this part of we're talking about the top, as we change the path when we're at a different location, we're going to have a different speed. So let's see what that looks like by drawing a new free body diagram, but now at the bottom. At the bottom, I have my force of gravity going down. Water still, or gravity still pulling the water down, obviously. But now the pail is pushing up on the water. So here they're going in different directions. But really cool at the bottom, they are still both in the centripetal direction. So therefore, we would say, I personally like to always make the direction of the acceleration my positive, so I would say force normal is positive here. And so the question is, how is this similar or different to what we were doing with the other one? So the way that it's similar is that it's still the same two forces. They're still in the direction of centripetal, but earlier they were working in the same direction. Now one of them's working against the centripetal and one of them's working for it. And so therefore we have a negative here. We can then rearrange this to see at the bottom. It says, once again, what is the force exerted by the pail at the bottom? So how would that be changed? We take this formula. We say force normal is now equal to mv at the bottom squared over r. This is going to become a plus mg. So force normal would then be equal to mv at the bottom squared over r plus g. So the big thing is just the sign change. Because the sign changed up here, it also changed down here. Yeah, and so that is kind of looking at this example of the pail that is being swung in a circle.